Hi everyone, my name is Fouad Matin, and as Alyssa said, I'm talking about building a high-performance dynamic CDN with Next.js. So first, a little bit about my experience with Next. I will not be back. First, a little bit about my experience with Next. I've been using it in production since early 2017. I made Create Next app while working with it a lot during my time at Segment, and now I'm working on a fast, privacy-first personalization API called User Mirror, which I'll briefly mention during my talk. The main project I'm here to talk to you today about is Help Users Vote, a set of simple tools for companies and brands to help their users vote. Here's what it looks like on some example websites. It's a banner at the top of the page that teams can customize without using any code to match the look and feel of their website. So what do companies expect from us? Well, first and foremost, to protect customer data. It's been pretty popular in the news recently, given some revelations, but even if it's anonymous, that is our #1 priority. 2, fast rendering for above-the-fold content. That's things like a banner that gets rendered at the top of the page or a modal that gets displayed once the page has finished loading. And 3, fault-tolerant, reliable APIs that they can depend on. The majority of this talk is going to be about the second expectation and how do we adapt Next to fit our performance needs, but we'll briefly mention how do we solve the other two towards the end. Cool, so before we get into it, why do we actually care about speed? Why is it worth our time? And a 1-second delay in page load correlates to a 7% drop in conversions and an 11% drop in page views, which means how many people are actually sticking around to wait for the page to finish loading. So clearly, every second and every millisecond really matters. Now, what are our goals? First, 200 millisecond response times across all APIs, whether it's HTML or JSON, and then personalizable experiences for our users. So that means if we had a banner up today, it would say 23 days left to register to vote in San Francisco, which is a PSA for all of you San Francisco residents. If you plan on voting in this June's election, that is a real number. You actually have to register in the next 23 days. It's a little PSA. And now to get into how we're actually going to accomplish those goals. First, we're going to talk about designing our system. On most days, the user request flow looks something like this. A user goes to the partner site, and from our perspective, nothing really happens. But on days like election day, that partner website will load our embed script, which kicks off a process of loading personalization and configuration data out of User Mirror, passing that to Next to actually render the banner, and then the embed script actually takes that HTML and CSS and injects it onto the page. Cool, so that's more or less what we plan on accomplishing today. Now we're going to talk about speeding up our Next.js application, starting with an out-of-the-box setup with Create Next app. We run Next build and then Next start, but that brings us to our first question of how do we actually measure if and how well it can scale? There are a lot of different ways to do this. Ultimately, what you need to do is send a bunch of requests at a certain rate limit and then time how long it takes the server to respond, and then compare it against different rate limits. So we decided to use Hey, which is a HTTP load generator written in Go as a replacement for Apache Benchmark, but you can really use anything here. And that's how we get the data to generate these graphs. So you can see 100 requests per second in purple, 1,000 requests per second in yellow, and in pink, 10,000 requests per second. And we set a timeout of 2 seconds. That's why you see the graph actually tapers off. It's because we didn't want the lower numbers to actually get overshadowed. But out of the box, we come in with a maximum request per second that we can handle of 950, which isn't bad, but given our goal of handling a lot of different popular brands on a single day, we really need to close the gap between 10,000 requests per second and 100 requests per second in terms of response times. So this next point applies to all React applications. Out of the box, whether you pass in Node-env or not, you're kind of using the development version, which means you're using an unminified version of the React JavaScript, and it's allocating extra objects, which are helpful for debugging, but not so helpful for our users who are just trying to download our site. So we're going to go and pass in Node-env production, which helps both client-side. Next build handles this out of the box, but for our server, we want to keep the memory usage pretty low so we can handle more requests. But that got me thinking, well, how big is React? So the minified and gzipped version of production in React is 32.7 kilobytes, which isn't a lot when you're based in San Francisco and you have a fast internet speed. But when you're on a 2G network, which is 40 kilobits per second, that's 6 seconds. That's 6 seconds of your users just downloading React, no dependencies, none of your application code, just React. So we wanted to try to solve that problem. There are a few React-like libraries that you can swap in, like Preact, which comes in at 3 kilobytes, obviously a lot smaller than React. We're We're going to go and test it out by passing in the using preact example argument to create next app, run npm run build, npm run start, and see how that impacts our performance. So we have a pretty big performance increase in terms of requests per second. We're at 1390, which is really good, extra 400 requests per second that we can handle. But if you look at the right side of the graph, all the numbers actually bumped up a little bit in terms of response times, which is an okay trade-off to make in some situations, but we really care about that initial render to be really quick. So we're going to try another library called Inferno, which is a little bit larger than Preact, but really focuses on how do we make it more performant. So that's what the extra 5 kilobytes is for. We do the same thing, using Inferno example argument to create next app, npm run build and start, and we're going to see how that impacts our performance. Wow, okay, so now we're at 1950. It's escalated pretty quickly. We're already double what we started with, and our response times are starting to look a little bit more stepwise. So our P99 response times, which are on the far right, are no longer getting timed out, and we're responding to all requests within a second, which is good, but still not 200 milliseconds good. Now, we could keep tuning our next app, but we want to take a more holistic approach and see where can we tackle the low-hanging fruit across our application. So we're going to talk about using the right tools for the job. Going back to our goal of 200 millisecond response times across all APIs, some of you were paying attention to that slide about speeds. Notice it was actually about page loads, not response times. So why not time the total page load? And that is a good point. So I opened up Chrome DevTools, turned on 2G throttling, and opened up the network tab, and then refreshed the page. 6 requests happened. The DOM was ready in 400 milliseconds, but the page didn't finish loading until 47 seconds. So what were we actually doing if all the content that we care about, the HTML and CSS, was already there? We were downloading a bunch of JavaScript that we don't need. In our use case, we are just providing HTML with a link in it, and we want some CSS to make it look interesting and compelling. We don't actually need the JavaScript. So we got rid of it. In our custom document file, which is _document.js, in your pages directory, we remove the head and next script tags. And our new load time is around 100 milliseconds, with the DOM being ready in 200 milliseconds. Again, remember that we're no longer actually sending the script tags that we're also taking up some more of our HTML. The takeaway here is that you don't always need JavaScript. Really understand what your use case is and what you can get away with. Now, even if you do need JavaScript, like for our modal, for example, that gets rendered after the page is finished loading, we build a separate static bundle that has no external dependencies, so we're able to keep that really small. Going back to our user request flow from earlier, let's dig into what is the user mirror API doing in all of this. It's really 2 things. One is personalization, so that's the if you're in San Francisco based on your IP address, then show 23 days left to register to vote. And then configuration, which enables anyone on the partner team to change the color of the link from red to blue or the background from black to white. Cool, so in our getInitialProps, we're going to go and make a request out to user mirror. Again, this could be any API that we want to use, but really what we're going to see here is as requests come in, we're going to dispatch a new request, and we're going to see how that impacts our Next.js performance. Really, really badly is the answer. We got down to 160 requests per second, which is so much worse than where we started, and our requests are going up through the roof and timing out again. So not ideal. The takeaway here is every network request has a huge impact on API performance, especially when you have a single-threaded environment like Node, where requests are coming in. We then try to dispatch Next to render the React, which then kicks off a getInitialProps, which kicks off another request. It's just this chain that Node isn't well suited for. And so we're going to swap in the data fetching for a Go service that we wrote, that you can think of it as taking the getInitialProps out of our Next app and moving it up a layer in our stack to something that can handle those open connections a little bit better. So let's see how that small change impacted our performance. Boom, we're back on track, over 2,000 requests per second. Our response times are reasonable again. Not quite what we want, around half a second, but a lot better than we were a few moments ago. So that got me thinking, well, why not write everything in Go? But got some Go fans. This is a little bit of a slippery slope because then you start thinking, well, why not Rust? Because I heard Rust was really fast and that's all the rage. But why not C? Because that has to be fast, right? It just has to be. And we could, and I have no doubt that many people in this room could write a really good HTTP server in C, but that's not our goal. Our goal isn't to write an HTTP server in C, it's to help users vote. And in order to do so, we need to provide HTML and CSS very quickly to our partners. Now, luckily for us, someone already built one. It's called Nginx, and it's really, really good. So just use that instead. Which brings us to our next topic of caching dynamic content. So Nginx is a HTTP proxy written in C that you can put in front of your services to kind of help with that connection load burden. And a nice benefit is that it comes with a cache built in. So we can pass a TTL, which is time to live, or how long things will stay in the cache, of 24 hours. And then we're going to see how just that small change impacts our performance. Wow, OK. Well, we achieved a quadruple increase in terms of the number of requests we can handle. That's actually having the data fetching happening at the Go layer and then passing it off to Nginx to serve those requests really quickly. Our response times are continually making a downward trend, which is awesome. And we're starting to close the gap between the purple bars and the pink ones. But we're still not quite there yet. So why don't we put Nginx in another place in front of our Go service with a TTL of 30 seconds because we want the changes here to roll out really quickly. If you have a homepage banner on example.com and you change the color from red to blue, that should change quickly, which then passes off to the next app that is actually getting those properties via the query parameters. So we'll see how that double Nginx proxy actually impacts our performance. And boom, we have 12,000 requests per second. So we're already starting to handle way more requests than we did out of the box after a few pretty simple changes. And now our response times at the P99 level are around 300 milliseconds, which is pretty good just coming out of a few minutes. So the takeaway here is just avoid building infrastructure wherever you can. There's a very easy tendency of, oh, OK, well, I could just hack this together really quickly in JavaScript or in Go. But odds are someone has already thought about that problem more deeply and had to close more Jira tickets than you would have ever wanted to. So just enjoy the fruits of their labor and get to solving the problems that you actually need to solve. Now we're going to talk about how do we make it faster and more private across the country. All of the tests so far have been where a server is hosting all of our services, and then another server is acting as our client, making all these requests. But that's not how it's going to work in production, right? That's not what reality looks like. We're going to have users all across the country who are trying to access our server, and no matter where we put it, ultimately our bottleneck is going to be how close our server is to our users. That's where a commercial CDN like Cloudflare comes in. They have 33 edge servers across the United States and over 140 globally. And they just released a new product called Workers, which lets you run JavaScript on their edge servers. So now, why do we care about that? Why is that actually useful to our problem? Well, for companies and brands who want to render our banners server-side, we can route their servers to the same cloud provider and region for speed and cost efficiency on the bandwidth level. And then for users who might be accessing our content via an iframe, we can route their browser to the nearest region, so we're storing data about them as close to them as possible before we delete it. Cool, so let's see how that looks in our API diagram. We have Cloudflare on the front door, so a user will connect to the closest Cloudflare edge, which then gets routed to the nearest version of our cluster, which is running on the major cloud providers and regions in the United States. Cool, and now what's next? I'd be remiss to not have at least one pun about Next. And before we get there, I started thinking after doing all this work, well, why not build static bundles per config? So when I actually change the color from red to blue, why don't we just create some new HTML or CSS or JavaScript then, rather than having to do it dynamically? And that is a good point. It would have saved us all a lot of time. Here's what our API would look like. We have Cloudflare sitting still as our CDN with aggressive TTL and timeouts, which then is hitting our compiled scripts. But something to know about CDNs in general is that they're designed to handle and work with slow origin content. So we could have whatever we wanted sitting behind Cloudflare, or you could use Nginx as our equivalent of a CDN, and it's meant to handle that. And really what we want is to have a quick turnaround between the changes that we make that are relevant to the user, so personalizations, for example, making it to our content that we're serving to the users. But then that got me thinking, well, why are we making these network requests at all? Given that we just have some static HTML and then some parameters that are getting passed in based on who the user is. So again, this is knowing what your constraints are. And for us, we can expose a NPM module that people can install at helpusersvote/React, where people can bring in our React components and then hit our JSON API separately in order to render the personalizations. The takeaway here being limit the data you send over the network. If you're a consumer app, then you can use service workers like Next offline to actually render content without needing to hit your servers. And Now, about that data that you still have remaining, like really, what does it mean to be dynamic? It means to respond to the user who's currently accessing that content. So really, all we have left is that we're sending over the network is user-specific data. And there's been a lot of talk about how do we think about this as application developers. And I think ultimately there are 3 principles that I like to use for approaching this problem. First, store data as close to your users as possible. 2, process data in the same region where it's stored, so you're avoiding that extra hop of moving data around. And then 3, delete all user-specific data when you don't need it anymore. Now, this won't solve all of your regulatory obligations, but this is a good step towards getting the right mindset for approaching that problem. What does this mean for us? Well, we're hosting a version of our infrastructure in every major cloud provider and region in the United States to make it as fast as possible for your users. And we're helping our largest partners run our infrastructure on their own servers so that they can ensure and audit that data stays anonymous and everything is deleted after the election on November 7th. So if you want to help your users vote in 2018, check out what our banners look like on your website at helpusersvote.com. And if you want to use our personalization infrastructure for your business, and check out our launch in 2019 at usermirror.com. Thanks. If you have any questions, feel free to find me in person here for the rest of the day or on Twitter at Fouad Matin. Thanks, and have a great Zeit day.